Hello. Welcome to today's lesson on understanding the variation in current, potential difference, and resistance in a parallel circuit. Today, we will start by covering how current splits at junctions in a parallel circuit. We will then look at how voltage behaves in a parallel circuit. Finally, we will explore how adding more branches affects the total resistance in a parallel circuit. So far, you have gained a solid understanding of how current, voltage, and resistance behave in series circuits. You've learned that in a series circuit, the current is the same through all components, the voltage divides among the components, and the total resistance is the sum of individual resistances. Building on this foundation, we can now delve into the unique characteristics of parallel circuits. This lesson will deepen your understanding of electrical circuits and how different configurations affect the behavior of current, voltage, and resistance, enhancing your broader comprehension of physics principles. Let's get started. In a parallel circuit, the behavior of current is markedly different from that in a series circuit. Let's continue with the hallway analogy we used in the previous lesson, but this time imagine there's a junction where the hallway splits into multiple paths, each leading to the same destination. At the junction, the group of people representing the current is divided among the different paths, but all paths eventually merge back at the same endpoint. Each path represents a branch in the parallel circuit, and the number of people choosing a specific path determines the current in that branch. Some paths might be wider, representing lower resistance, allowing more people to pass through, while narrower paths, representing higher resistance, let fewer people through. Despite taking different routes, the total number of people entering the junction equals the total number exiting it. This illustrates the conservation of charge, which means the total current entering a junction equals the total current leaving it. For example, if 3 amps of current enters a junction and splits into 2 branches, with 1 amps flowing through one branch, then 2 amps must flow through the other branch. The currents in all branches add up to the total current entering the junction, ensuring conservation of charge. Now moving on to voltage. In a parallel circuit, the behavior of voltage is quite different from what we see in a series circuit. Let's go back to the analogy of people representing electrons, walking down hallways. This time, imagine that at the start of each hallway, every person is given the same number of tickets, representing energy at a ticket booth, the power source. No matter which path the person chooses, they receive the full number of tickets. As the people move down their chosen paths, they encounter checkpoints, representing components like resistors. At each checkpoint, they hand over all their tickets. This is like how in a parallel circuit, the components in each branch use up the full energy, voltage, supplied by the power source. Now let's compare this to a series circuit. In a series circuit, the people would walk through multiple checkpoints, representing components, and each checkpoint would take a portion of their tickets. So, by the time they reach the second or third checkpoint, they have fewer tickets left to hand over. This means the energy is divided across components in series. But in a parallel circuit, each branch receives the same amount of energy per electron, just as every checkpoint, or component, gets the same number of tickets from each person. Note that this doesn't mean that each component receives the same total amount of energy. Remember that different hallways might have more or fewer people walking down them, representing different current in each branch, meaning the total number of tickets collected in each hallway will vary based on how many people take that route. So, in a parallel circuit, the voltage across each branch is the same because each branch is connected directly to the power source, and every electron receives the same amount of energy. This is equivalent to each person receiving the same number of tickets from the booth. However, the total energy used in each branch varies depending on the current, how many electrons are flowing through that branch. This is equivalent to a different number of tickets being collected in each branch, due to different numbers of people going down each. Let's solidify this with an example. Imagine you have a parallel circuit with 2 components where the battery supplies 10 volts. Since the voltage is the same across branches in a parallel circuit, The voltage across the first component is 10 volts, and so is the voltage across the second component. Now let's explore the concept of resistance in a parallel circuit. In a parallel circuit, the relationship between the number of branches and the overall resistance works differently from what we see in a series circuit. Imagine a road with heavy traffic where there's only one lane open. The cars, representing the flow of current, have to squeeze through that single lane, which creates congestion resistance. Now, imagine the same road but with multiple lanes open. The cars can spread out across these lanes, which makes it easier for traffic to flow and reduces the congestion. In a similar way, adding more branches to a parallel circuit creates more pathways for the current to flow. When more pathways are available, it becomes easier for the electrons to move through the circuit, so the overall resistance of the circuit decreases. Even though each individual branch still has its own resistance, the combined effect of adding more branches reduces the total resistance. In summary, in a parallel circuit, more branches equals less resistance. This is because adding branches provides additional pathways for the current, making it easier for the electrons to move through the circuit. There's a formula for calculating effective resistance in a parallel circuit, but this is beyond your GCSE specification. If you're up for a challenge, pause this video and use Ohm's law and what you just learned about the behavior of current and voltage to derive it. Let's apply what we've just learned to an example. Imagine a parallel circuit with a voltage supply of 12 volts and 2 branches. The first branch has a resistor R1 equal to 4 ohms, and the second branch has a resistor R2 equal to 6 ohms. We want to calculate the current flowing through each branch, through R1 and R2. The first step is to identify the values given. We have values for voltage across the power supply and the resistance of the 2 resistors. We can calculate current through each branch using Ohm's law. First, we need to recognize that the voltage across each branch in a parallel circuit is the same as the supply voltage, as we have just learnt. Hence, voltage across R1 is equal to voltage across R2 equal to 12 volts. We can now apply Ohm's law to each branch. For the first branch with R1, the current equals voltage over resistance, which is 12 volts over 3 ohms, giving us 3 amps. For the second branch with R2, the current equals voltage over resistance, which is 12 volts over 6 ohms. This is 2 amps. The current through the first branch is 3 amps, and the current through the second branch is 2 amps. This also tells us that total current in the circuit is 3 amps plus 2 amps, totaling 5 amps. In today's lesson, we examined the behavior of current, voltage, and resistance in parallel circuits. We learned that in parallel circuits, the current splits at junctions, with the total current entering a junction equal to the total current exiting it, illustrating the conservation of charge. We discovered that the voltage across each branch remains the same, regardless of the path the current takes. Additionally, we explored how adding more branches to a parallel circuit decreases the overall resistance, providing more pathways for the current to flow. Finally, through an example, we applied these principles to calculate the currents in different branches and verify the total current in the circuit. Next lesson, we will move on to comparing series and parallel circuits.